Okay, we're given the function y of xt that you see here, 0.01 meters times 9.6 radians per second times t minus 0.04 radians per meter times x. And we're asked to verify that this satisfies the wave equation. Well, whether this is a harmonic wave with sines and cosines or not, it could certainly satisfy the wave equation. Okay, now let's observe a couple of things. We have units here, and the units were distraction when we did this, so I kind of erased the units and did everything without units. But let's address the units real quickly. Okay. What you have here is going to be radians per second times t, radians per minute, per meter times x. So you're going to have units of t's in seconds of radians here, and if x is in meters, you're going to have units of radians here. So you're going to have a consistent unit throughout here. Now you're going to get a unit of radians squared, but radians are kind of a funny unit. When you multiply them by meters, they tend to become meters. Or when you divide them by meters, they can tend to become meters. And you can kind of hand waving. I don't want to get into the details of how we could reconcile this or what kind of situation. You might actually have something like this arise. I'd have trouble coming up with a situation. I don't know that it would arise in any meaningful situation, this kind of a function. But the idea here is just to show that this function satisfies the wave equation, and with a little hand waving, the squared radians multiplied by the meters here could end up with the result of meters. So it's not inconceivable that would work. And the units actually work out if you carry them all the way through, as far as verifying that the second derivative of y with respect to t and the second derivative of y with respect to x, which we calculate over here, have the relationship that they should have. Now, what should that relationship be? Basically, that relationship is just that the second partials be in a constant ratio to one another. Now, that constant ratio is related to the speed of the wave, and we didn't actually address that in the session we had, but we'll address it here just to make sure we understand. Okay, well, we calculate the partial derivatives. Again, I did this eliminating the units, but this is going to have units of meters, and this will have units of radians per second, and this is going to have units of radians per second. So we're still going to have meters times radians squared per second squared. That's going to be, in this case, this is going to be in radians per second. This is going to be in radians. We're going to have radians squared times meters over seconds. That's going to be the units. Now, the derivative is straightforward, just using the chain rule, and I'm not going to go through that. We have the square of this function. The derivative of this inner function is 9.6 radians per second. And then we have 2 times this function for the derivative of the square, 2 times this. Similarly, for the partial of y with respect to x. Then, taking the second partial derivative, we take the derivative of this. This is just a linear function of t, if you're taking the derivative with respect to t. We simply get this result. The units will be meters here, and radians squared per second squared here, which is going to give us meters per second, meters per second squared. Down here, our units are going to be, again, meters for the 0.01, and radians per meter for the x derivative. Okay, so we're going to have radians squared per meter squared here. Now, the partial derivatives are straightforward. If we divide one by the other, we can get the ratio, and we can see that the second partial of y with respect to x is going to be 0.04 squared over 0.96 squared, or 0.04 over 0.96 quantity squared, times the second partial of y with respect to t. The units here, well, we have 0.04 radians squared per meter squared divided by 0.96 radians squared per second squared. And what are the units of that ratio? The units will be second squared over meter squared. Okay, and those are units of 1 over c, where I use c for wave propagation velocity. Okay, now if we go into the reasons for the wave equation, which we discussed in terms of the bead model and so forth, you can review that. We see that this ratio ought to be the reciprocal of c squared, not c. Okay, c having units meters per second, reciprocal of c squared is going to have units second squared per meter squared. The wave equation is second partial of y with respect to x is 1 over c squared times the second partial of y with respect to t. Alternatively, second partial of y with respect to t is c squared times the second partial with respect to x. There are, again, reasons for that you should think about, but that's how you answer this question in any case, and a little bit more of the context of the question.